So, first of all, thank you very much for receiving me in the RISC-V day. I'm Christian Duran. I'm going to introduce you to hardware for trusted execution environments, or TEE, for RISC-V implementations. This work is made with the collaboration of the University of Electro-Communications, UEC, the National Institute of Advanced Industrial Science and Technology, AIST, and the Technology Research Association of the Secure IoT Edge Applications based on RISC-V Open Architecture, TRASIO. This is the outline of the presentation. First, we will introduce our work in a general scope. Then we describe the process of a trusted execution environment. We will describe the implemented hardware to conform the system from a general perspective, and in a detailed manner regarding the crypto cores and other hardware modules. Finally, we will show the chip results and conclusions of this presentation. So let's jump over the introduction of the TE hardware. The TE hardware system is a hardware generator based on the Chisel-based chipyard framework. The chipyard is maintained by USC Berkeley and is a conglomerate of hardware generators and RISC-V cores to create a fully customizable environment, to make it easy for small teams to design, integrate, simulate, and type out a custom system on chip, or SoC. The cores integrated include the rocket chip, the Berkeley auto-ordered machine boom, and the 8 series Ariane core. The project also includes FPGA accelerator like Hacha, the Gemini, and the NVIDIA Deep Learning Accelerator. About the TEE hardware, a repository based on chipyard generators. This repository contains the necessary crypto cores and accelerators to execute trusted execution environments. You can download it from GitHub in the list shown. The current version supports the running of a secure bootloader together with a Linux embedded in our SD card. The software can run a simulation using Verilator, and also can run the following FPGA boards. The demonstration included the elaboration of the root of trust in a zero-state bootloader and the procedure of hashing and signature of the Linux to run. But first of all, to understand the application of the hardware built in a system, we must talk about the root of trust and the trusted execution environments. We use Keystone, a TE hardware framework, which includes the interactions with the root of trust in higher privilege levels. An example of a trusted execution environment is the authentication of a device and a client-server key creation for a symmetric cipher. In this environment, we have two participants: the remote PC, which performs the attestation, and a host allocated in the secure environment. The connection can be done using OR or UART or a TCP connection. Keystone builds a trusted environment using a chain of trust that is distributed in multiple levels of executive privilege. The chain of trust starts with the root key stored securely inside of the silicon, named silicon root of trust. From here, the execution of any procedure must be signed using this root key across different execution modes, such as machine mode, supervisor mode, and finally user mode, where the host resides. The TE allows the program to create an enclave application on the trusted side from the untrusted side of the execution. The explanation of the procedure is as follows. First, the client on the PC makes the connection to the enclave host. This host program cannot be inside of the untrusted side, so the enclave application is activated using the Keystone API. This interfaces with the Keystone runtime named area, which runs supervisor mode. The enclave application then communicates to the secure monitor, or SM, in machine mode. In the second step, the verification will create the hash and sign of the enclave application. In this information, the application makes an attestation report to the enclave host, then is sent to the trusted client. This client checks the attestation report for verification. Here you can see different hashes and signatures of the previous process. The attestation report contains the hash and signature of the secure monitor and enclave app, along with the manufacturer's public key. The previous hashes and signatures come from the procedure of the root of trust. The device key is first verified by the client, which is supposed to be generated using a manufacturer key. But for now, it's stored in the FSBL. The security monitor is verified in the second step, which is signed using the device secret key in boot procedure. Finally, the enclave application is signed using the secure monitor secret key and verified with the public key. Now, the following step for communication is to establish an exchange keys for asymmetric cipher. Because now the client has successfully verified the host, each environment will create their public secret key pairs where only the public key is sent to the channel. Now, the communication is secure and authenticated. In this example, the keys generated are created using SSH. The demo consists of communication stream sent and reply to the verified host. The host will always reply with the number of words in the message sent. It's a very simple demo. This memory map shows the cryptography in the proposed system. The upper row is the crypto accelerators memory, and the second row is the main system memory. First, the Linux image is the secure monitor of the embedded in the DDR, depicted in S, which is streamed to an SHA hash crypto core. The hash value HS is stored locally in the crypto core memory. Then the 825519 base point multiplier is used to generate the public and private the public secret keys SK and PK. SK is stored in a write-only memory, while PK is stored in normal memory. The final verification is performed by signing using the CURE 25519 calculation. The final result is stored again in the normal read-write memory, right here. Now we can talk about what is inside of the TA hardware system. First, we'll talk about the implemented system and chip architecture. We implemented a core flex of several RISC-V processors supporting integer, multiplication, and floating point operations, which are necessary extensions for Linux to be compatible. These processors can be either the Rocket core of the Boom core. Right now, the Boom version 2 is implemented in the master branch of the repository. Right now, the Boom version 3 is not used due to its instability problems, but the same implementation exists for the version 3 in different branches of the repository. The coreplex contains several implementations of the tiling bus to act as a system, peripheral, and memory buses. Attached to the memory bus, the system contains regular input-output devices like GPIO, multimedia, car controller, UART, USB, and PCIe. It also contains the memory devices for programs and data such as the max room, the SPI room, and the DDR controller. The crypto generators are also attached to the peripheral bus, whose configuration and data input and output are memory mapped using register routers. The following table introduces the configurability of the hardware generator. Right now, we support three different types of FPGA, named the Xilinx BC707, the Altera 4, and the TR4. You can set you can set these extensions as word size of the processor that you want to implement. You can also set the hybrid configuration of the processors. Either you want two rocket cores or two Moon cores, or an hybrid implementation of the two. The size and clock of the memory bus is also configurable. You can put it in 64 bits or 32 bits. And the inclusion of the PCIe external peripheral is also possible. Here we illustrate how the different processor configurations are displayed using Linux. You can see the processor architecture inside of the CPU information changes whenever we build a different hybrid implementation of the Rocket and Boom processors. The ISA configuration and the word size is also reflected as well. This table reflects the logic utilization of the BC707 FPGA with different processor configurations. The biggest utilization is the two Boom core configuration, which occupies just over 50% of the logic utilization. Every configuration with boom and rocket processors have over 40% of the smallest of the hardware with 2 rockets. While 2 rockets have 30% of the FPGA. You can achieve smaller configurations down to 20% with just 2 rocket cores in 32-bit, supporting only integer multiplication and atomics. Okay, so let's dig right into the details of the crypto accelerator course. So the crypto accelerator course included the SHA-3 accelerator for hashing, the AD25519 accelerator for generating the keys and signatures, the IS encryption, and a true random generator. Sorry, I skipped. No, I didn't skip. The crypto course can be brought to from the peripheral bus to be implemented as a custom instruction using the ROCC. AES support both 128 and 256 bits and can be changed on the fly. AD25519 contains 2 separate accelerators, namely the AD25519 multiplier and the AD25519 sign for pair key generation and certificate verification, respectively. The PRNG is done using the for now a linear feedback shift register, but we developed this PRNG based on the ARM Trustzone RNG programming model. This tableau reflects the logic utilization of the crypto course. The biggest core implemented here is the AD25519 signing accelerator. We constrain most of the logic because of the arithmetic multipliers. The AD25519 base point multiplier also contains arithmetic multipliers, but the resources certainly are bigger in the memories that need to handle, where the generated secure keys are stored actually operated, both the public and the write-only memory. The SHA-3 and AES are purely logic implementations, so they don't have any memory implemented. In ASIC, the area of occupation is also consistent. The AD25519 is the biggest because of RAM utilization. The other 3 cores are purely logic implementations without the need of the RAM. And most of the power utilization is used in the AD25519 signature. The execution environment was tested on a system using both pure software and hardware accelerator implementations. The process to authenticate the payload mostly uses the SHA-3 hashing, leaving the AD25519 K-pair and signing as an additional calculation process. As we can see here, the hardware solution decreased about 2.5 decades of the execution time compared to the pure software approach. Here, we show the output of the verification operation using SHA-3. The acceleration can output up to 30 megabytes per second. It's about 270 times faster using compared to using purely software. So as for the other hardware models, we contain an SPI ROM, which is an option to have the bootloader in an external device. This is ideally for debugging multiple binaries in early stage bootloaders. The system says the reset vector in the 10,000 or the 20 million address. Always in the 20 million address resides the zero-state bootloader. And in this case, disable the QSPI, the boot room will contain the CSVL and cannot be changed. This is the scenario for release hardware where the authentication process needs to be secure, as the boot room needs to be not writable indeed. For debugging, we recommend you activating the QSPI, where the boot room is a simple snippet to jump into the 20 million address. The other device is the memory controller, which is strongly synchronized to match the clock of the DDR external controller. In this case, we can shrink the bus and use different clock domains for external bus control. The intention is to have flexibility at the moment of using any external IP for the main memory. Usually, the memory controller handles a different clock and bus size. Particularly in our case, the IP can use a 64-bit Xe4 interface for the VC707 and a 32-bit Avalon bus for the Altera boards. So finally, I'm going to show you the silicon results. The previous protocol was implemented several times in a ROM 180 nanometer process. The first version contains a 4-core rocket chip-based platform where the crypto cores are not included. The size of the die is 4.5 times 7 millimeters. It draws about 390 milliwatts at the maximum frequency of 92 megahertz. Another version of the platform with 2 cores, 2 rocket cores, was implemented in also room 180. This includes the SSH3, AES, 82.519, QSPI, and USB 1.1. Bringing the necessary devices for performing acceleration in the trust execution environment. The size of the die is 4.5 times 4.5 millimeters and draws about 706 milliwatts of the maximum frequency at 98 megahertz. There's a photo of the TE hardware demo. It interfaces the chip with the FPGA for the DDR controller. Both of the chips do not actually have the DDR controller built inside, but we decided to accelerate the main memory tunneling port. With this, the PCB connects to a tunneling port inside of the FPGA, which contains the DDR controller. So finally, to conclude this presentation, there are the final remarks. In this presentation, we show a hardware generator for trust execution environments. The hardware implements several crypto cores, which include SSH3, ED25519, and AES, as well as several peripherals for input and outputs, and also memory controllers. This hardware generator is configurable according to the needs of the final application. It is also capable of choosing the RISC-V cores to be used and the ESA options. We tested the design in several FPGA and also was implemented in a 180 nanometer technology. We demonstrated also with that the time of execution for TE tasks using hardware accelerators drops significantly compared to pure software implementations. We want also to acknowledge the New Energy and Industrial Technology Development Organization, NEDO. The presented work is based on results commissioned by it. So this is all for my presentation. So I am now open to questions. Thank you very much.
Thank you very much. Please submit the question from audience to Slack channel. So, okay, I have a question. So, you taped out 2 rocket core version, right?
It's right here.
Yeah. So you also plan hybrid core combination with Boom and Rocket, or Boom version 1, version 2, version 3?
Right now we already submitted a version 2 Boom with Rocket. Yes, that was about, if I am not mistaken, maybe three or 4 months ago. We should be receiving those chips soon enough to actually make the measurements. But yeah, we already submitted the fabrication for that configuration also. Yeah, that's right. The size is about the same. We only removed one rocket core and introduced one boom core, but the boom core is configured to be the smallest possible. I know that maybe the boom is not supposed to be small, but for now the intention of the demo is just to make a demonstration of the soul of the security capabilities. So, for example, I think the boom that we fabricated, if I'm not mistaken, only has like it's really small, like 16 kilobytes of cache with very low TLBs. I think they only have like 256 TLBs implemented. So actually, the misses of the architecture maybe are going to miss a lot. But yeah, we have also that one implemented in ROM 180 and soon to be delivered here for measurements.
Thank you. Is there any question from audience? So, okay, question from me. So you use FPGA Stratix 4, and I don't know, Boom version 2 or version 3 core can be occupied in FPGA or just conceptual.
Yes. So we actually implemented even 2 cores in the FPGA, occupying more or less half of the whole FPGA. It's pretty big. I mean, and those are normal booms. I mean, the ones that you can find by default in the chip jar configuration. So if I'm not mistaken, those are uses 1024 TLBs with a much bigger cache. I think it's 32 or 64 kilobytes of data cache. It's possible. I mean, even we have more room for putting more implementation. The one that probably is struggling to have the boom inside is also. I mean, those are results for BC707. The one that the one for the experience that had struggling to actually fit inside of the PGA is particularly the DE4. The DE4, once you put a core, a boom core, there's little space for another kind of hardware. Even we have to put some of the hardware in the DE hardware as well to make it fit or make the boom smaller. With the current version of the demo, makes the boom smaller to make it fit in the D4 demo right now. The BC707 doesn't have any problem, and you can see it's only 50%, even in the maximum configuration that is the RISC-V 64GC. So yeah, right now it's difficult to put inside of the Altera boards for now. At least the Altera board that we have here. That's all.
Thank you very much. Is there any question from audience? No? Yeah, Christian Duran, thank you for your presentation. So we apologize to change the time slot.
No, it's okay. I actually interpreted what you say in Japanese, and trying to actually came here to do the presentation to continue the RISC-V day. So yeah, so maybe I will be leaving right now. So thank you very much for listening to me. Thank you for having me here. 日本語を使うで、まだできないけど、本当ありがとうございました。
ありがとうございました。